Okay, in this video, we're going to see a few examples from the L'Hopital's notes. Most of this document will be covered in class, but for the sake of time, we'll put a few of the examples into this video. We're going to start with the proof of L'Hopital's rule. I'm looking at the rule right here in the yellow box. We need to show that given one of the sides of this equation, we can show that it equals the other side. Keep in mind that we are working in a situation where it is already known that f of a is equal to g of a in that they are both 0. Okay, that's going to be important for the proof. All right, proof is on the next page. We're actually going to start with what was the right side of the equation on the previous page. Let's start with a limit as x goes to a of f prime of x over g prime of x. Now, typically with limits, if we're able to plug in the x value that we're approaching into the function itself, we should do so. So we're going to start with that step. We're going to replace these x's with the a value that x is approaching. And now we have f prime of a over g prime of a. Each of those, top and bottom, is a derivative. Let's replace them with the limit definition of derivative that you learned in Calc A. I'm actually using the alternate form of limit definition, both top and bottom. So f prime of a, for example, becomes limit as x goes to a of f of x minus f of a all over x minus a. You'll recognize this as the limit of the slope formula from algebra. With this new ratio of limit definitions, we can do some simplification. The x minus a's drop out of both top and bottom, bringing us to this next step over here. This is where it's important to remember that we're working under a condition where both f of a and g of a are known to be 0. So we can effectively remove those two terms, and all of a sudden, we're done with the proof. We now have our original limit is equal to limit as x goes to a of f of x over g of x. From here, we're going to skip ahead to the next page and look at the one-sided limit example. This is a quick one. Didn't really need to see it in class, but it's worth seeing now. Basically, the same rules apply for these problems if you're working with a limit from one side. Here, I've got x approaching 0 from the left. It doesn't really change how I'm going to approach this thing. I'm still looking at my original expression and realizing that if I were to try to plug in a 0 top and bottom, I would get the indeterminate form of 0 over 0, which is no good. I am going to pause then and write out my justification of why we can use L'Hopital's rule, where I'm just pointing out that both of these limits, top and bottom, are 0. So from there, I can proceed back up to my line of work here and take derivatives top and bottom. Sine becomes cosine. X squared becomes 2 over x. And now we try once again, can we plug 0 in for x, where I'm appearing to get now a 1 over 0, which is not an indeterminate form. Limits that appear to be evaluating to 1 over 0 are interpreted as infinity. We do have a negative sign to consider. As I move towards 0 from the left, this quantity 2x would be negative quantities. All the x values to the left of 0 are negative. So I do have to be thinking about that in order to get this negative sign here and give an appropriate final answer of negative infinity. Feel free to look at a graph of this function and see for yourself that as you approach x equals 0 from the left, you are approaching an asymptote that we go towards negative infinity. All right, we're going to skip now to the very, very last problem in the notes. I would recommend actually that you try this problem on your own first and use the video just to check your answer. All right, so jumping over in 3, 2, 1. All right, here we have a limit as x goes to 0 of sine of x to the x. As you're going to see very shortly, trying to plug in here gets us to an indeterminate form of 0 to the 0, which is an exponential indeterminate form. And therefore, we need to bring in both e and logs to be able to solve this one. We're going to replace sine x to the x with log sine x to the x as an exponent on e, okay? Um, in this next step right here, I'm using a log property to bring x out, at which point I kind of stop. You could see there's more work here, but that work doesn't really become evident until we've done all the other work below. So we pause here for a moment and we focus just on this exponent, x times log sine of x. What happens to that exponent as x approaches 0? So that's the work that we're seeing down in the next line. Okay. Right away, I still have to correct this expression in order to get one of the indeterminate forms that plays along with L'Hopital's rule. So I want to force this thing into a fraction, which I can do by dividing the log by 1 over x instead of multiplying by x. And right here now, we're at a spot where if you were to plug in zeros, you're going to get infinity over infinity. 1 over 0 in the bottom, there's an infinity. The top, sine of 0 is 0, at which point we have log of a value approaching 0. Think about a log graph. As you approach 0, you are approaching an infinity. Granted, it's a negative infinity, but that doesn't really matter here. So from this step, before moving forward, we jump down to the third line and show our justification for L'Hopital. Both of these limits are infinity. And I can jump back up and start worrying about derivatives. It looks a little complicated, but it's nothing you can't handle. Derivative of 1 over x is negative 1 over x squared. Derivative on the top, we do have to think about chain rule. Okay, a log derivative is going to see us using 1 over the original input to the log, so 1 over sine, but then we're multiplying by the derivative of sine, multiplying that on to give us a cosine. Okay. In the next step here, I am simplifying things a bit. I don't like working with fractions inside of fractions, so moving from this middle step over to the right corrects those issues. In fact, I can go even a bit further and replace cosine over sine with either a cotangent in the numerator or, as I chose to use, a tangent in the denominator. Okay. From here, let's try to plug in again. Plugging in zeros. Now I've got the 0 over 0 indeterminate form. So I'm going to show a second set of justification for L'Hopital's rule. And then we're going to take derivatives again. Negative x squared becomes negative 2x. Tangent becomes secant squared. And finally, after all of that, we can plug in zeros now and get something usable. In fact, I get back a 0. This is not my final answer. We have to remember that all of this work below the first line was analysis of the exponents in our original limit after having brought in the e and the natural log. So this 0 is not a final answer. It becomes the exponent on e. My final answer then, e to the 0, is actually 1. As always, you can graph the original function, see for yourself as you approach 0, y is approaching 1. Okay. Reminders at the bottom, L'Hopital is not the same thing as quotient rule. In fact, L'Hopital is easier. We're just treating the numerator and denominator as separate exercises to differentiate. Okay, so just keep that in mind. If you have any questions, feel free to email me or ask me in class. Thanks for watching.